Let's create a video on testing a second order PWM DAC low pass filter. These are the parts that came in your kit. We have a 2K and a 2K for 4K, and I've wired them together like that. It's a bit ugly. And we need two 5.6 millihenry inductors. These are the big resistor looking things in your kit with this color scheme. We're going to use the 1 nanofarad capacitor again. It's right there. We connect everything up, ground, -1 minus, 2 minus. 2 plus is the output of the capacitor. W1 and 1 plus are connected to the input. So let's go to our network analyzer, right? And you can keep everything the same, just run it. Except now we'll try to find the omega naught. Because I've got it here, it's better just to try to find the phase close to 90. Okay, so the phase is very close to 90 and the magnitude is minus 2.47. The Butterworth would have it at minus 3, right? Minus 6 would be critically damped, and anything less than that would be overdamped. So this is an underdamped system. It's not exactly what we want as far as Butterworth conditions, but it will work as a PWM DAC. We do have some parasitic issues in the higher frequency domain, which we can see. But let's go first and the cutoff frequency was around 48 kilohertz. So let's look at this on the oscilloscope, and we can see we see some underdamped response there. Now you'll notice there is something going on with the input. Oops, I'll just get that out of the way a little bit and we'll just zoom in. Alright, this does have high frequency harmonics, but there is a little notch type filter going on there. Alright, even with this setup, it's hard to avoid the voltage division due to the 50 ohm series resistance of the Scopy. But you would see this on anything. Alright, so that's 5. Right, now something else we can do is, that's the first 50 terms of a 50% duty cycle square wave. We can go into our signal generator math, apply that, and we should almost see the same. Now this is filtered a little bit differently because it doesn't have infinite harmonics, right? It only has 50. Alright, so let's see what that looks like for regular square wave, and we will take it to 50. And we can see that it is in fact starting to filter. And we can, but we're going to see these little ringing when we change states or go from high to low. Alright, but let's put in this buffer. can see, oops, I need to take that to 50. You see it's relatively the same. Let's take it to 100. And it's filtering, but you might notice there's this little ringing there. Okay. And I'm going to take it up to 500. And now we have to really zoom in to see. And now it's mostly ringing, right? It no longer looks like a sine wave. That's because we're at such a high frequency that at 500 kilohertz, right, the first 50 terms are hitting our non-ideal section of the low-pass filter. But we can put it in math as well. Go up to 500. And it might look a little bit better, but that's because we're not taking as many harmonics. All right. Now, something interesting is that, well, what if rather than filter, an ideal filter would have had this coming straight down, the phase staying minus 180, but it didn't. Well, what if we never sent those higher harmonics? So what one can do is let's only take the first up to 13. Just copy and paste. Make sure to put the parentheses there. Apply. Go back to the oscilloscope and see it's a little bit cleaner. In fact, we can go at 500 megahertz. Right. It's not a perfect sine wave. This is still has that shape, but it gets slowly. It gets better than having all those harmonics. Okay. So what you can see is that I think at 300 shows it maybe a little better. I'll turn that off. You can still see these ripple, right? But the peak of the output wave is still greater than that ripple. And I think right about 400, the ripple and the peak is the same. And so in fact, due to that effect, the output ripple, which is effectively the number of bits you can have, right, that goes into that equation, it gets worse with higher frequencies due to this going on out here. So anyway, an interesting thing is that do you create your PWM DAC with a digital synthesis tool and use less harmonics, and then it'll actually you'll get a better performance, or maybe find resistors, capacitors, inductors that are more ideal. These particular ones are not ideal, but you can really see what's going on. So your mission would be to do all that steps in the video.